Hello, in this video we are going to work with planes. I should begin by saying that this is one of the primitive concepts that we cannot really define like a point of a line or a line, but definitely we have an intuitive idea of what a plane is. We would say that it's a flat surface, it is infinite in all possible directions, and that it doesn't have any thickness. We're going to work with planes, and for that the first thing we want to do is to find a way, or more than one way, of writing equations of planes, so having equations that can tell us exactly whether a point belongs to a plane or not. Let's begin with a picture over here. This is my plane. I'm going to call it pi. And I'm gonna assume that I know a point in this plane. I call it A, and also that I know two vectors, and those vectors, we're gonna say that there are vectors parallel to the plane. That means that if we move along them, once we start on a point that is on the plane, we stay on the plane. So we want two such vectors. One of them I'll call them V, and the other one call them W. I'm gonna use A as a starting point of those vectors, and the condition that I want to have is that those two vectors V and W are parallel to pi, but they are not parallel to each other. So for instance, this one over here is W, so V is parallel to pi, W is parallel to pi as well, and V is not parallel to W. Okay, so this is my claim. Any other point on the plane that I want to reach, I can do so by considering a linear combinations of vectors parallel to V or W. So what do I mean by this? Let's say we have a point here, let's call it P. If I want to travel from A to B, I can do so by considering some number lambda multiplying the vector V plus some number mu multiplying the vector W. So lambda mu are real numbers over here. So this is say that we can write the vector AB as a linear combination of V and W. So my vector with starting point A and endpoint B can be written in this form. Okay, so how can we do this for any point on the plane? And well, let me see over here. I'm gonna make a line parallel to B, parallel to the vector V, and going to the point B. Okay, very light line over here, and I'm gonna make another line parallel to the vector W and going to the point B, something like that. Okay, and now I'm gonna take, this is my vector lambda V, and here this is my vector mu W. And you see I did this in such a way that A and B are opposite vertices of a parallelogram with sides parallel to V and W. So I achieve what I wanted of being able to travel from A to B along vectors parallel to V and W. What I did over here, it can be done for all point B belonging to the plane pi. So this means that we can actually use this idea to find all the points that we want on our plane pi. So for any point B on the plane, like I have here my B, is if I consider the position vector for this point B, so let's say R. I'm saying over here that I can write this position vector as the position vector for the point A, and then the sum of the linear combination of the vectors V and W. We can write R as OA plus some lambda multiplying V plus some mu multiplying W, where lambda and mu are two real numbers, which are two independent parameters. So this is the vector equation of a plane. You can also use a normal vector to write the equation of a plane. So let's say we have our plane pi over here, and let's say we have a vector n, which is normal to the plane. Being normal to the plane means that it's normal to any vector of the plane. So any vector v parallel to the plane that I consider is perpendicular to n here. Okay, so how do we do this? Let's say we consider the position vector of any point on the plane, so R over here, and then we consider the position vector of any fixed point of the plane, let's say point A over here. Then when we consider the vector going from the endpoint from A to the endpoint of R, then we have that vector is perpendicular to n. So that is the condition that we want. That means that when we consider n dot product R minus OA, this has to be equal to 0. Remember, the dot product is 0 when the vectors are perpendicular, and I'm writing the vector going from A to the endpoint of R as R minus the position vector of A. So this is another way of writing the equation of a plane. From this same way of writing the equation of a plane, the normal equation, we can move on to the Cartesian equation of a plane. Let's assume that the vector n is given by coordinates a, b, c, and let's say that the point A is x, y, z. So if I substitute those values on the normal equation of the plane, I'm going to have that a, b, c dot product, and then over here I'm going to have x minus capital X, y minus capital Y, and z minus capital Z. So here the small x, y, and z are just the generic values of for the generic vector R. This has to be equal to 0, which means if I apply the dot product, that A times small x minus big X plus B times small y minus big Y plus C times small z minus z has to be equal to 0. And this can be written as ax plus by plus cz is equal to actually a number, that is ax plus by plus cz for the capitals x, y, and z. So we can just actually write this as a constant d, and we got the Cartesian equation of the plane. Just simplified form will be ax plus by plus cz equals to d for some constant d, where the values a, b, and c come from the normal to the plane that we consider. Let's practice writing the equations of planes in the different ways that we know now. Let's begin by assuming that the plane that I'm going to call pi is such that the points A equals 1 to 0, B equals -1, 2, and C equals 0, 1, 3 belong to the plane pi. So it's enough to have 3 points to determine a plane. So you have A, B, and C, and then we have the plane pi, including them all. I'm going to write the equation. If I want to write the vector equation, I need to fix one of the points. Let's use A, and then I need two vectors, but I can, for instance, look at the vector going from A to B and the vector going from A to C. We can write the coordinates of these vectors. For A, B, we are going to have -1, that's -2, -1, -2 is -3, and 2 -0, 2. So that's my vector AB. And for AC, we have 0, -1, -1, 1 -2 is -1, and 3 -0 is 3. So those are my vectors. So I'm going to write that the position vector of any point on my plane R is equal to, and then I have position vector for A is 1, 2, 0, plus some parameter, for instance, call it lambda, times the vector -2, -3, 2, plus mu times the vector -1, -1, 3, where lambda and mu are real numbers. So this was the... Now, actually, if I want to do the cross product of AB times AC, then actually my vector n is going to be the perpendicular one pointing in the other direction according to the right-hand rule. It doesn't matter, any of them pointing in one direction or the other is going to be good for us. And if we do this vector product, remember this has a formula that is rather complicated, and take your time to check that this actually is -7 for -1, the coordinates of the vector normal to the plane. So now, for writing the equation in the normal form, I'm going to write -7 for -1 dot product, and then we have the generic vector r minus 1 to 0 is equal to 0. We have here then the normal equation. If we want to now write the Cartesian equation, we just need to actually do that dot product that we have in the previous form. So we are going to have -7 for -1 dot product x -1 y -2 z, and this is then -7 is multiplying x -1 plus 4 multiplying y -2 minus z is equal to 0. If we rearrange this with everything that has x, y, and z on the left-hand side, we have -7x plus 4y minus z is equal, and then we are going to have -7, because this is plus, and then plus 8. So -7x plus 4y minus z is equal to 1 is the Cartesian equation for our plane.